So now we're going to talk about concavity, which still has to deal with our derivative, but this is actually going to be a little bit more specific. So in our definition, if you are given that a function is differentiable, on an open interval, then f is said to be concave up. Concave up. And the good news is, if you're sitting for the AP or even for any of my FRQs or whatever, you can use this notation. It is recognized. Okay? On the open interval. So your function is considered to be concave up on the open interval if f prime is increasing on that interval. Okay, I have a quick question. If I wanted to know if a function was increasing, what did we just do? Oh, we took the derivative. So if I want to know about concavity, it says that f prime is increasing. So what do I have to do to f prime? Oh, I have to take the derivative. So what is this then? Second derivative. Concavity is the second derivative. It's the slope of the slope. Okay. So then f is considered to be concave down, or CD, on the open interval if f prime is decreasing on that interval. So what we're looking at is f double prime. Okay, it's the slope of the slope. Okay, so as I said before, when we're reading a graph, we are reading a graph from left to right, true? So what we're looking at is what is happening to the slope of the slope. So here we are. Right here, my slope is very negative, then just slightly negative. It changes to 0, then becomes positive, and then even more positive. So if you think about what's happening to your slope as you move from left to right, it goes from a lower value to a higher value, which means your slope is increasing. Does everyone understand what I'm saying? So we're going from a very negative value, let's call it negative, negative. Then here we have a negative value, then changes to 0, then becomes positive, and then really positive. So you're looking at, over time, what is happening, because you're looking at what is happening to this graph. Because clearly that is concave up. You agree? If you just look at the graph portion without the slopes, concave up like a cup, right? So the slopes are increasing. If you are reading the graph from left to right, here, this is very positive, then just a little bit positive, turns to 0, then negative, then very negative. So that means the value goes from a really high number, let's say in terms of slope 5, then maybe becomes 1/5, then goes to 0, then negative 1/5, then negative 5. Okay, so your slope is decreasing. Okay, again, as you read from left to right. Okay, so we left off talking about concavity, and this is one of the statements that you would actually see when you would be reading a question. So you might see something to the effect of, let f be twice differentiable, or f is a twice differentiable function. And I know that's not spelled correctly. It should say differentiable, not differential. But what that just means is that you can take at least the second derivative of this function. So this is an important statement. Granted, it's spelled properly. Okay, so what this says here is, if your second derivative is greater than 0 for every value of x on that open interval, then the original function f is concave up. Okay, on that interval. So what you're looking for in terms of concavity, again, is the sign. If the second derivative is positive, then the original function would be concave up. If the second derivative is negative, then your original function is concave down, and I'll use a notation CD. Okay? So this is what we're going to do. we are going to use our original function that we talked about increasing and decreasing on the previous page, and we'll talk about concavity. So on the previous page, we found the first derivative, which was 3x squared minus 6x. In order for us to determine concavity, we then need to take the second derivative and find our critical numbers from the second derivative. So this would be f double prime of x is equal to 6x minus 6. We want to set this equal to 0, and in this case, because this is a first degree function, it doesn't matter if you add 6 and divide by 6 or you factor out a 6, it doesn't make a difference at all. So I'm just going to factor out a 6, leaving me with x minus 1 is equal to 0. So this is my factored function, more specifically the second derivative, and this is what we would use if we were plugging in the values on the intervals. So here's my number line. We'll be using f double prime here. And what's my critical number? X equals 1. Okay? So what is the multiplicity of 1? Even or odd? Even or odd? It's odd. X minus 1. Multiplicity is 1. Yeah. So that means this sign is going to be what? Positive. And this sign would be negative. If you don't believe me, here we go. I'm just going to pick over here, let's pick 0. That's the easiest one. 0 minus 1 is negative 1 times 6, negative. Everybody good? Okay, so this is concave down, and this is concave up. The reasoning or justification for this would be f double prime is less than 0, and this one is f double prime is greater than 0. Okay, so here we have to provide the interval or intervals over which f is concave up and concave down. So we could say that f of x is concave up from what, 1 to infinity? Because why? Yep, f double prime is greater than 0. Then we would also say that f of x is concave down. I just use the notation. From where to where? Yep, negative infinity to 1, because f double prime is less than 0. Okay, questions on concavity? Okay, in addition to determining the intervals over which our function is concave up and concave down, we can also determine what's called points of inflection, whether we just use the x-coordinates or we actually have to find the original points. So if you have this continuous function by definition, okay, f is continuous on the open interval, okay, containing some given x value, and if the function changes the direction of concavity at a given point, then we would say that f has an inflection point at x equals 0. Or excuse me, x sub 0. Okay, so basically what this means is we're identifying the x-coordinate where the concavity is going to change. Now, we can also state that there is a point, meaning x comma y, which is what this is, and it is an inflection point of f. Okay, so this sounds repetitive, but what you might get is a question that would say, provide the x-coordinates, coordinates of the inflection point, or provide the inflection points. So either way, you have to read what it's asking for. They might ask you for just the x-coordinate, which is definitely the easier, because then you just have to provide x equals. But then if you wanted the actual point itself, how do I get the y value? Plug your x value where? Into the original, because look at this notation. It says f of x sub 0. Not f prime, not f double prime. So you'd have to plug into the original. All right, so inflection points occur when f double prime changes from positive to negative or negative to positive. Okay, here's the other thing. You want to say the least amount possible. So when you give a justification for either an x-coordinate or an inflection point, you don't want to say F double prime changes from positive to negative and negative to positive. You just say F double prime changes signs, period. Okay, so what they're saying here is, if this is where your function is concave up, and then your graph changes to concave down, where this occurs, meaning right here, is your inflection point. Okay, and this also occurs when it's in the other direction. Okay, so just kind of keep that in mind. All right. Does anyone have any questions on concavity?